For all those people wondering what I've been up to in the lab, this is what I've been working on. I'm going to go through this step by step and give an illustration of what's happening in this circuit. I'll break it down into a bunch of different sections, and we can have a look at each section, and some sections I'll briefly describe what's going on and provide some scope shots and things like that. And then when we get into the HHO spark gap, there's going to be quite a bit of information to absorb on that. That's what I've been working on mostly in this circuit. Okay, here's the sections that I'm going to break it down. We'll start with section 1 here, the step-up transformer, and I'll describe to you the function generator and how this is running. Then take a look at this section here. This is basically a voltage multiplier. Then we'll move on to the step-down transformer. Have a look at that, discuss that. I'll touch briefly on this area here. Basically it's a voltage doubler. Then finally we're going to dive into the HHO spark gap, how it's designed, the tests I've been doing on it, the results I've been getting. Okay, back to the part 1. Basically what we're looking at here is a step-up transformer. What I have done is just used a regular 120 volt wall transformer that steps down to 12 volts, and I've turned it around. Now what I've done is I've added a cap onto the primary. So essentially what I'm doing here is creating a tank circuit. Now you'll notice there's a diode, there's a battery, and there's a transistor, and then a function generator. So basically the positive of the function generator is used to drive the transistor, which is an NPN Darlington pair, which I'll show you in a bit. And then there's my supply, shown in the first test, are 12 volts, just to have a look at what's happening in the transformer. To get a little more detailed on this setup, you can see there's a diode in there. So what happens is the pulse goes to the capacitor, and I match the frequency and get a resonant tank circuit going on there. And basically I use as little as I can from the supply by using a standard resonant tank circuit. Now we're going to have a look at the hardware. Basically here's the transformer. You can kind of see one of the transistors sitting in the back. Again, normal wall transformer, 120 volt down to 12 volt, and what I've done is I've just turned it around, giving us a standard step-up transformer. Here's one way to drive this setup. Here I have a 555 basically function generator going on here that provides a square wave pulse. I want you to have a look at where the diode is located here. This diode is going to the base of the transistor, and I always use a diode here so that I don't get anything coming back into my 555 setup. Sometimes those back EMF spikes, they can actually go over the reverse voltage of the transistor and come back into your timer circuit and end up killing your timer circuit. But because I don't want to fool around adjusting this 555 timer, I'm just going to use a regular function generator. It gives me basically the same results. Here's another shot of the hardware. That bridge rectifier I'm not using, but basically you could kind of see where the scope is hooked up on the end. Here, the output. Now we're going to have a look at my scope. Basically you can see we have a dampened sine wave. This is what's coming on the output now of our transformer. As well, here's the amperage. We're showing about 90 milliamps to drive this unit. Okay, let's discuss this sine wave. Right now I am actually pulsing it through a spark gap, and so the sine wave looks positive, but what's happening is the tank circuit is resonating, and that's what's giving us a sine wave on the output. Okay, let's dive into the voltage multiplier. Basically what this does is this takes half of the wave, of the sine wave, and puts them together, and each stage here increases the voltage. But as the voltage increases, the amps drop. There's a direct correlation between the two. I played around with this a lot and found out that I need some pretty good capacitors on here, and in the drawing I only show one diode. The hardware actually consists of two 007 diodes in series for the first two legs of the circuit, and then three of them in series for the third leg. As well, the capacitors, there's three of them for every one that you see on the drawing. They are parallel, rated for 3000 volts. Okay, moving right along here. Hopefully I'm not boring anybody. Right here is what I call my recovery unit. What happens basically here is when the spark fires, electrons are allowed to flow. It causes a pulse. So again, we get the same thing, a positive pulse going through the primary, and I have a cap on there to try to oscillate so I can get as much energy back on the secondary side as I can. The secondary side steps down. This is a very important part to this circuit. I have tested different types of transformers here. It looks like I am going to have to wrap my own. The one I'm using right now is just a simple little Radio Shack one. It seems to be providing good results though. But again, this is a crucial part, as well as the HHO spark gap. Okay, on to the voltage doubler. Essentially what this does is on the step-down transformer, when we get oscillations, those oscillations of course are felt on the secondary. So what I'm doing is I'm taking those oscillations from the secondary, and when I get a positive oscillation, it goes into the cap on the top. When I get a negative oscillation, it goes into the cap on the bottom. Now because those caps are hooked in series, that means that we get double the voltage. So if I get 100 volts in the first cap and 100 volts in the second cap, together the output of this doubler is 200 volts. Now you're probably wondering why I used a step-down transformer. The reason is I want to take now my high voltage and I want to turn it back down to amps. I don't need 1000 volts going back to those batteries or back to my primary driver. I want to bring it down so I have lots of amps, so those are fairly big capacitors. That way I can push amps back into my source. Okay, a super fast review. Here we have an oscillating tank circuit that's driving a step-up transformer. Now my tests, I've ended up using 36 volts to drive it, and the 36 volts gives me basically 400 volts output peak to peak. Now the output from the transformer goes into the voltage multiplier. Now the voltage multiplier takes the 400 volts peak to peak, makes them 800 volts, and pumps them up to over 2000 volts. Now because of standard loss, we can't just take the 800 volts and times them by 3, but basically I'm getting around 2000 volts on my measurements. Now that again, when the spark gap fires, we end up here having the same thing, oscillating tank circuit with a step-down transformer. My step-down transformer is giving me back about 200 volts. I then use the voltage doubler here to take peak to peak side, so 200 and 200 on each side, so I got about 400 volts that I'm putting back into my supply. Yes, I did say 400 volts going back into the supply. My supply is only 36 volts, but remember, increase in voltage, decrease in current, plus losses. So there's no over unity here at all. Well, it looks like my 10-minute time limit is almost up, so I'm going to close by saying that part 2 is going to be the HHO spark gap. We'll look at where it all began, findings that I've found, where it could lead us.